everyone. Welcome in. We are so excited to get started with you today. As folks start coming into the Zoom room, go ahead and get situated in your Zoom window. The first thing I'd like to ask you to do is to navigate to the bottom of that Zoom window, and you'll find a button that looks like a chat bubble. It says chat, and if you click that, you'll be able to type a message to the participants as well as today's presenters. That is how we're going to be asking questions today. Both Tom and myself will have an eye on the chat bubble, so please feel free to drop your questions in there. We only ask that under that to section where you can select who can see your message, please set that to everyone. That way we don't look like we're talking to ourselves. So make sure everyone can see your chats, and that way we can kind of share the wealth of information, see who's thinking what. So to go ahead and get started, navigate to that chat bubble, make sure you have set your responses to 2, and then let me know in that chat bubble. Let's see, what's a fun question? What were your Super Bowl plans? What did you get up to for the big game? I know that I went over to a friend's house and I actually got to introduce a new friend to the rest of my friends, so that was fun. But would love to hear what you all were up to. Oh, we have an educator grading papers. I totally get you on that, Patricia. Ooh, watercolor painting. Okay, very nice, very nice. Awesome sitcoms. Love that. Friends over, stayed home reading. That's awesome. Watched with the family. Ate snacks and watched commercials. Sleep, yep, I totally get that. And I don't know if you all follow us on Instagram, but before the big game, we did post a reel showing how you can use Vernier sensors and software to study the throwing of a football. So if that sounds like something you'd be interested in, check out our Instagram. Now, it is just a minute past the hour, but I want to make the most of our time together today, so please feel free to keep using that chat bubble, but I do want to hop into some housekeeping items first. First and foremost, you will receive a recording of today's webinar. It usually takes us about 3 to 5 business days to get that ready, so keep an eye on your inbox. We will get it to you as soon as it's edited and uploaded to our website and YouTube channel. In that email with the recording, you will also get a link to our resources folder. In that resources folder is today's presentation. You can go ahead and open that and follow along. We also have a certificate of attendance and some free experiment files for you. So I'm going to drop that in the chat as soon as I'm done talking. And the other thing I wanted to let you know is we want to answer your questions today. So please use that chat bubble. Let us know what you're wondering. If we happen to not get to your question, please feel free to reach out to us via email. You can reach us at physics@vernier.com. With that being said, I will pass you off to today's presenters. Thank you so much for joining us.
Well, hello and welcome. So I'm going to just go on with the presentation here. I'm Fran, so I'm the one on the left there, and I taught high school for about 20 years, grades 9 through college, mostly physics, a couple other things here and there, and I'm excited today to talk about simple harmonic motion. Tom?
Tom, I'm the guy on the right, and I've only taught for 9 years, Fran, so you have over double the experience in the classroom as I do. I did spend some time in the Coast Guard, though, so I have been around the country, literally, actually the continent a couple of times on the icebreaker Polar Star. But I'm glad to be here working in chat. And with that, I'll mute myself and pay attention to what's coming in.
I think that's amazing to have circumnavigated the continent, but anyway, simple harmonic motion, definitely an awesome topic, super relevant to physics because you're doing simple harmonic motion and then you're talking about how that relates to waves, and it's talking about, well, if you've got things that are vibrating, so which is something that atoms do and molecules do and all kinds of things do everywhere. You've got these little vibrating motors, which are turning, circular motion into vibrating motion, and it's everywhere. So simple harmonic specifically is motion that occurs when there is a net restoring force that is proportional to the position, to displacement, and in the opposite direction. So our two examples today are going to be mass on a spring and an approximate simple pendulum. Not only is our simple pendulum approximate, but simple pendulums are only approximately simple harmonic motion. You got to keep the angle small, and whether or not you talk about the small angle theorem depends on what level your students are. And then with simple harmonic motion, the displacement with respect to time is represented by a sinusoidal curve. And we've got a little illustration there that you'll see again. We're not going to start with that though. We're going to start with the simple pendulum. I hate this illustration. It's in our book, Physics with Vernier. This is from, I forget which number experiment with it, but we put it in the file, the Google file for you. It's called back and forth motion. And so with back and forth motion, that experiment looks at a number of different motions that move back and forth and compares them and contrasts them. And some of those motions are simple harmonic or approximately simple harmonic, and some of them are not. And so it's an interesting thing for students to take a look and see if they can identify those patterns and distinguish what one motion is compared to another motion. So we're going to do this. So I'm going to stop sharing that screen, and I'm going to share a different screen instead. And now I'm over here. So I have here set up a pendulum, and this pendulum, you'll notice, has two strings. And it's one string, but I just have the ball in the middle of it. And the nice thing about having two strings is that it makes your motion really stay in the same plane. Most times if you have a pendulum bob hanging from only one string, at least in my experience, it doesn't stay going straight back and forth. It'll start to rotate and twist. And if you're doing that with a sensor, you'll wind up getting out of the range of your sensor, whether you're trying to track the period of the pendulum using a photogate, you're going to make it's gonna start hitting the edge of the photogate, or in this case with the ball, you're going to wind up having it not in the range of the motion detector, which is what we're using for this particular experiment. And I've tried this experiment with a bunch of different things that were not this particular ball, which is about 3 inches, 5 centimeters in diameter-ish. That's more than 5 centimeters. That's more like almost 10 centimeters in diameter. Sorry. So wait, I have a ruler here. Not here. It is. I'm going to call it 9 centimeters in diameter. Anyway, if I've used things that are not a ball, like a big hanging mass, or I tried it with a book to see if a book would kind of like stay flat, they don't work. But this works, and it's big enough that the ultrasound from the motion detector is going to bounce off of it. And to set this up, what I do is I actually use this little box to make sure that the sensor of the motion detector is at about the same height of the equilibrium position of the ball. And so to do that, I happen to have a convenient little cardboard box here. I'm going to connect this to graphical analysis, and we're going to go ahead and collect some data. So let's push the power button. I got my little blinking red light, and gotta figure out my sensor data collection here. I'm using the web app. I don't know if you've noticed that, and you connect slightly differently with the web app than you do with the installed app. But especially if you've got Chromebooks in your classroom, then you're using the web app. If you're using tablets or you're using computers, then maybe you're using the installed app, but they look pretty similar. And we're going to use the motion channel on here. You might find it convenient to switch to motion cart for this. But I'm gonna leave it on motion, which works well, works just fine for this particular setup. Those two channels are basically a difference in the amplitude of the ultrasound. How loud it is, though of course being ultrasound, we can't actually hear it. And the motion cart is less amplitude, and it actually is a little bit better when you're measuring something that's a little bit smaller. So we will use that mode with the mass on a spring. But anyway, got this, and it's not going to do me no good going this way, so I have to have it this way because that's the direction that this is going to move in. Need to move it a little ways back, and I'm going to go ahead and that. Oh, what's happening here? Let's try this. Oh, I know what happened. God. This is the one I want. And there's two apps here, and I accidentally clicked on the wrong one. It doesn't want to do this. Anyway, so I'm going to go ahead and start this moving. Let it settle a little bit because there's always going to be a little bit of wobble in these things to begin with. And once it's been going for a moment, that's when I'm going to hit the collect button. And here I'm getting my really nice sinusoidal curve. So what do you notice about this curve? One of the things that I notice is that I forgot to zero the motion detector with the ball at equilibrium. And I noticed that because I've got this curve is above my zero equilibrium position. So I'm going to redo this. I'm going to first have that not move and go ahead and zero it. And then I'm going to get this moving again. All right, let it settle again. Looks pretty good. And collect data again. And now my sinusoidal curve is very nicely going up and down, about equally up and down, excuse me, compared to the zero line. So I can make this bigger if I like. That actually looks pretty nice. I'm very happy with that. What would I do with this now that I've got this? I can think of a lot of things that I can do with this data. First thing I want to do actually is I want to look at the velocity data. So I'm going to make this two graphs, and it automatically comes up with velocity, and I'm going to expand that as well. And it's interesting if you go ahead and drag a line across this to see, well, what's happening in each part of the graph. So if I'm looking at my position graph, if I'm at the maximum value, so that's going to be farthest away from the motion detector, then the velocity, it's actually zero at that point. And then if I go along to the point where the position is at the equilibrium position, the velocity is at its fastest negative velocity there, which negative because it's going towards the motion detector. And then if I keep going to the closest position to the motion detector, that's when it stops because the velocity is going to stop moving and come and turn and go the other direction. And then there it is at the equilibrium position again, and that's when it has fastest positive velocity away from the motion detector. And this kind of thing, being able to do that analysis with students so that they can look and see what's happening at the same time in both the position and the velocity, that I think really helps when you're able to go step by step at those particular times and see what those two values are. I think that's helpful. And this is something that, you know, you can play around with this doing different things. You might also look at, and you can do acceleration either on a third graph or on the second graph. I kind of like to take velocity off this graph and put the acceleration on, because when they're right next to each other, I really feel that it's easier to show what's happening. That if you are at the lowest value of the position that you're at the highest value of the acceleration. And that when the position is at equilibrium, the acceleration is at its minimum, that there's the least amount, the least magnitude of acceleration. And then similarly, if you go to the positive point, then we're at this negative acceleration. And what does it mean to have a positive acceleration and a negative acceleration? And those are confusing concepts even to seniors in high school. Acceleration is because it's the second derivative, because it's the rate of change of a rate. It's hard to wrap your head around. So I like to really talk about, all right, so what makes an acceleration positive, what makes it negative? Well, speeding up in the positive direction is going to be positive. And how do we define positive direction? Well, we're measuring from the motion detector. And so everything's going away from the motion detector in this direction is going to be positive, and then going towards it is going to be negative. So if you're speeding up in the positive direction, that's going to be this part from here to here is speeding up in the positive direction. So that's going to be positive acceleration. And then here, we're still going in the positive direction, but we're slowing down. So this part of the motion is going to be negative acceleration. And then we're going in the negative direction, speeding up, and the negative direction, but speeding up. That's a negative acceleration. And then I'm going to be going in the negative direction and slowing down. And that negative direction slowing down is going to give me what? Positive acceleration. So not only are you teaching about simple harmonic motion, but you're also reinforcing concepts that probably a bunch of kids were pretty confused about when you were doing them, when you were doing regular kinematics. So nice things to do if you want to go through the calculus and everything. You can. There are options. If you bring up the data table, and I'm going to move that a little bit, you could make from the position graph, you could make a calculated column where you're actually doing the first derivative and the second derivative of the position and compare those to the velocity graph and the acceleration graph, see how well they match. And if you've got your AP Physics C mechanics kids, or if you are teaching college, then this is the kind of thing that, it gives you the little bit of extra that you can do within the software that connects it to the math. How do we do? Do we have any questions at this point? I haven't paid any attention to whether we've got questions.
Yep. Fran, there was a question about which channel you're using for the motion detector. Did you say that you were using the ball?
Well, so on the not go direct motion detectors, your two channels are going to be human ball and then cart. And so this would be the human ball channel for this one, or human and ball. I guess you would have a human ball. Yeah, so the person and ball channel for this particular experiment. Anything else?
No, that's pretty much it. There is a nice share of a YouTube video talking about a resource that some people are enjoying using with their students from Hume and Ivy, and that's in the chat. So
Good old human Ivy. Good guys. Remember them well. All righty, so I'm gonna switch away from doing my pendulum here. If you are looking at the, if you were to look at the, and you know what, I'm just gonna go ahead and go back and share it. If you're gonna look at my presentation here, you will see that the next frame is, okay, now we're going to do mass on a spring. And we're still going to use the motion detector. I'm going to share the other screen again. Lots of screen sharing. I take that away. I'm gonna get this, I'll put that here, just because I wanted something a little bit taller. In this case, and I'm gonna put my motion detector here, and I'm gonna take this, yeah. Now, normally we tell you to put something over the motion detector so that this isn't gonna kill the screen, because you kill the screen and you kill the motion detector, right? You don't have to. You can also add somewhere here. I lost it. Um, Well, I guess I'm gonna use a little piece of string then. 'Cause I had a twist tie, and twist ties are great for this. Because you just take the little twist tie and you tie it together on there, but I'm gonna use a little piece of string. Twist ties are better than string. If you secure it with string, then it's much less likely that when students do that, that's gonna go flying off. Because no matter how many times you tell students, lift it up and then let it go, they are gonna pull down and let it go. Like that. And you really don't want that landing on your motion detector. So I use a piece of string. Notice it stayed attached, even though the whole thing went flying. And this is the time where I do want to change the channel. So if you have the old style motion detector that unfolds and it has the switch underneath, then you change it to the cart. And this one, we're going to go into the software and do motion cart. Which screen am I sharing? Am I looking at all you? I don't remember. So I'm going to do a new experiment. All right, yes, I'm sharing this screen, I got it. All right, so I'm gonna go in and for my sensor channels, I'm gonna change it to motion cart. You cannot do more than one channel at a time on this. This is not like the force sensor where you can do force and acceleration at the same time. You can only use one mode when you're doing this, which is fine. You only need one. You only want one position measurement at a time. You do not want more than one. That just gets confusing. So I'm gonna say done. And now, once again, this time I'm gonna remember, but if you don't remember, it doesn't matter because you can just collect more data. This time I'm gonna remember to zero the equilibrium position. And then once again, lift it up, let it settle a little bit so it's not wobbling all over the place, and hit collect. Right, and now I can expand that. Some of you may know that sometimes it's fiddly and you're not in a nice calm room that's pretty quiet all by yourself. You're in a classroom with 6 to 10 groups of kids who are all trying to do this at once, and it's pretty loud and they're chaotic and you can't watch all of them at the same time. And one thing you can do is you can give them an index card. So if your data didn't look as beautiful as my data looked, then this can help your students get some more beautiful looking data. And it will dampen the oscillation a little bit, but you're collecting for a pretty short period of time. The default is 5 seconds. So it's not going to dampen so dramatically that you're gonna want to do some kind of crazy combination of exponential equation multiplied by a sinusoidal equation. So here we have this very lovely graph. It looks very similar to the one that we were looking at before. Maybe it's because it's the same kind of thing. It is simple harmonic motion. Any questions at this point?
Yeah, there are a couple of questions, Fran. One had to do with curve fitting, so I hope you'll demonstrate curve fitting here in a moment. And there was another question that is related to that, which is, can you extrapolate a value beyond what you've collected based on curve fitting?
Ooh,
My
perfect.
hazy recollection is that you have to do a curve fit first to be
Yes.
able to do
Yeah.
that.
Yeah. No, those are great questions.
And then there's another one that I'll hang on to for a second until you've had a chance to digest those.
All right, so here's where I'm going to do my curve fit. So it's this little graph options menu down here at the bottom left that looks like a little graph. And then the linear is always the default because 95% of the time in physics class, you're using a linear fit, at least in my classes. So I'm gonna go up here and, I don't have to use sine. I could use cosine. It's gonna be the same. It's just gonna be off by, 90 degrees or whatever. 90 degrees? Yeah, 90 degrees. So there's my curve fit. And here it gives you the format of this. A times sine of bx plus c plus d. And then this is worth talking to your students about what all of those different constants are, the A, B, C, and D. The A, I think everyone understands that one the most, especially since A is the first letter of the word that it's talking about what part of the sinusoidal wave this is. Anyone? Anyone? I'm gonna look at the comments, see if anyone's saying that. No. Amplitude, yes. All right, you got it, amplitude. Everyone knows amplitude. And then D is also a pretty easy one. D it's just plus D at the end. When you ever got, if you had a function that was just anything like y equals 4, well, what's that mean? It means it's a line at 4 all the way across. So D, that's how much up or down your line is from 0. Okay, easy stuff. And then there's the B and the C that are inside the parentheses. So those are something that the sine function is doing something to. And your B, that's going to be your angular frequency. And yes, this curve fit does give you the angular frequency, so you've got a factor of 2 pi in there. And then the C, that's going to be your offset. So that's how much your sine wave is moved over from starting at time equals 0. Because of course, at time equals 0, the sine of 0 is 0, and you have to like do it goes up, and then now your sine is 1, and then it's 0, and then it's -1, and so on. So that's going to be your offset. So if you're not starting at with 0, that's going to say, all right, well, we're starting here and going here, or we're starting down here and not going up. So that's the whole thing. This one actually is surprisingly close to 0. That's just luck. Most of the time, that does not happen. Just so you know. So what was the question that you were holding off on, Tom?
It was looking for sources of springs that work well for this lab. There are
Well,
some recommendations out in the chat, but I didn't know if you had any specific ones that you'd recommend.
so the ones I'm using are actually the ones that came in this little box. We sell them. It's called Spring Set, order code Springs. And you get 6. They come in these little baggies. You get 3 that are 15 newtons per meter and 3 that are 5 newtons per meter, approximately. I would not count on it being exact. So this is actually one of the 5s that I'm using here because I'm using only 100 grams. If I were doing something more massive, such as my 200 gram mass, with my 200 gram mass, I might use one of my 15s because that's gonna like, if I try to use the 5 with the 15, with the 200 gram mass, then that's a pretty big difference. So it's, with the low spring constant spring, it's pretty easy to overstretch it. So if I'm using a heavier mass, I'll just use the one with the greater spring constant. And it's pretty easy to tell which is which, because one's floppy and the other one is not floppy. Floppy, not floppy. All right. So I saw someone in the chat, I was just glancing at it, mentioning a force sensor. All right, so let me. A very few of you, by the way, are on Blue Sky, and maybe you're following me on Blue Sky, and maybe saw my little sneak peek on Blue Sky, where I put this little meme up that I quickly put up today. So you can certainly put, not this force sensor, maybe this force sensor. You can mount the force sensor up here with the nylon screw that comes with it. And you can hang your spring off of that and then your mass off of that, and you can get some force data from that. Yes. And you can get force and position data from that. Okay. But the other thing you can do actually, I could use the other one again. I can tell which one it is now because I've got my little piece of string on it.
Fran, can you change your view so we can?
Oh, thank you,
see what's
thank you,
going on?
thank you, thank you. Oh, man. You haven't been watching what I was doing.
I was still reading the meme.
Ta-da! So you can have this hanging this way, or, I mean, you could do it this way. That works, you know, you can do that. Get force data, it works, it's just fine. I just think this is more exciting. Because this is the go direct force and acceleration. Ha. So I'm going to go ahead and turn off my motion detector and connect this. So disconnect my motion detector. Connect my go direct force acceleration sensor. Take a moment. There it is. There I've got more sensor channels, and there I'm going to put in not just force, but my x-axis acceleration. All right, done. And do a new experiment. Every time I change the configuration of the sensors, I have to do a new experiment. This doesn't really come up much in a classroom because usually with your lab, with your students, you're just having them do one thing. But if you're having to do multiple experiments, then you would have to do this, have to do that. So anyway, sensor data collection. I automatically get my force and acceleration graphs up here. So I'm going to go ahead and get that hanging there. And as I learned from forgetting the first time, I'm going to zero these sensors. I'm not going to zero the acceleration sensor. I'm going to zero the force sensor. All right. And then I'm going to let that start going up and down. And some nice simple harmonic motion. And collect some data. And again, I'm going to zoom to all data so I can see it. And once again, I'm seeing exactly the same thing. So we're seeing that not only do you get this graph for position when you've got this kind of motion, but you also get this graph for the force. And I think that's pretty key because ultimately, if your students go on in physics, they're going to be talking about differential equations, and they're going to be learning about how, this all relates together. and how it's important for things that are, vibrating in all kinds of different situations. Like when you've got, how do microwaves heat up your food? Well, what are they doing? They're making the water molecules vibrate. And that depends on the wavelength of the microwaves, and it depends on the characteristics of the bonds in the water molecule, right? And so that the characteristics of the bonds in your water molecule are like your spring, and there's forces that are going on, there's accelerations that are going on, and it all relates. I love physics. Did you know that? We can do curve fits on these. We could say, oh, well, does this match up with what we know about Newton's laws? Well, if you look at where you get a maximum force, you get a maximum acceleration. When force is around 0, you get, well, that's where you're getting about 9.8 for gravity, where you're at a minimum of the force graph, you get a minimum of the acceleration graph. It's super nice. And you can do this and say, all right, well, what was the period of this oscillation? 2 ways to find it, of course. One is to go ahead and do your curve fit and get it directly from your B data here with your factor of 2 pi, count it in, and you say, all right, well, that's my, do my period, and you got, because this is frequency, you got to inverse. And how does the period relate to the mass of your oscillating particle? Well, the cool thing about the force and acceleration sensor is you can change the mass by adding some. So I got these washers, and I can just put those on there. I can just put those on there. There we go. Harder to see the screw threadings when you're looking at it from the side. And now I have changed the mass. And if I were to get this going again and collect some data again, and I didn't re-zero the force sensor. I'm not worried about that right now. I'm thinking about, as I said, the period of this and comparing it. Can get that up there as well. So to look at period, what you can do is you can say, all right, well, here is one where I began, and here's 1 complete period. Here's 2 complete periods. Here's 3 complete periods. Here's 4 complete periods. And then if I use statistics on that, my range was 3.64 seconds for that. And so I take 4 periods, and they happened in 3.64 seconds. Well, now I can just do a little division problem and I know what my period is. And then if I look at the red trace, then I'm going to get rid of that for a sec, because for the red trace, I actually want to go over it and get a new time interval here. That's 1, 2, 3, 4, 5, 6. So we can already tell that it was quicker because I got 6 complete periods in here, where the other one I was only able to get 4 complete periods. Oops, didn't get that quite. Yeah. So I'm going to do statistics on that. And this one had a full 3.82 seconds for 6 repetitions. It's going to be a much shorter period. And then if I know how much mass this was, then I can start relating the mass and the period in some kind of relationship. So as you can see, lots of stuff you can do with simple harmonic motion with just a couple different sensors. I love this stuff. I would like to answer any additional questions that you have at this time.
Fran, do you mind showing them that extrapolation out beyond?
Oh, right. Thank you. Yeah, so let me go and make this graph bigger in terms of time. So now it goes up almost to 10 seconds. And out here, I don't know what's out there, right? So if I put the graph on, by the curve fit, I want a sinusoidal, they apply. Now, that keeps going. So if I were to interpolate, in this case, interpolate and extrapolate are doing the same thing. I can now take this farther out and get those values. I hope that helps.
Yeah, thanks.
All right.
There is a bit of discussion in the chat about using video analysis for this type of
Oh,
evaluation.
absolutely. Let me stop sharing. So I'm just actually looking at you. Yes, you can absolutely use video analysis. And in fact, in one of the video analysis books that we have, we've got two. One is on motion in sports, and the other one is conservation forces, conservation laws and forces. I think it's the second one that has the mass on a spring, and we provide, if you get that download, we provide several videos of masses on springs with different ones, and you can, there's little ones where you can figure out, okay, what is the spring constant of this spring? And then you have it going up and down, you just go and keep putting your dots on, going up and down, and yes, you get the same thing. So yeah, you don't need sensors to do simple harmonic vision. Other questions? Actually, at this point, since I'm no longer trying to share, let's see. What is the motion sensor's field of view? You're not going to be able to do circular motion with the motion detector. So the motion detector has basically you've got your you're coming out at a 30-degree angle. So it's 15 degrees on either side of coming straight out from it. So 30, 15 this way, 15 this way. And the way it works is because it's ultrasound, it's just going to emit the ultrasound pulse, wait for the first echo that comes back, measure that time and say, all right, that was the time for the sound going there and back. And I know the speed of sound and I figure it's probably room temperature in here. How far away is that thing? So if something's going in circular motion, sometimes it's going to be going sideways past it at a constant location, and sometimes it's going to be going away or towards. So that's not going to be great. If you're going to do something with circular motion, I would do that definitely using video analysis. Let's see, could one use the force sensor on the sensor cart and hang a stationary sensor cart and hang a spring and a weight from the stationary sensor cart while the motion sensor is below the bobbing weight? So, yes, it sounds like what you're talking about is if you had one sensor cart that was stationary and then another one and a spring connecting another one underneath. Is that what you're picturing? Sure, you could do that. Let's see. What about replacing the force sensor in Fran's demo with the sensor cart with hook attachment? Absolutely. Yep.
So it looks like you captured Stuart's comment well. And
Yeah.
I see that Dylan put a link in there to a survey to give us some feedback on the webinar.
Yeah, we're getting close to the end here. So let me go back to my presentation. So here's my presentation, and we're doing a giveaway. So all of you who joined us live have been entered to win a Go Direct motion detector, which is awesome. And it looks like there's a lot of you, so you got less of a chance of winning than usual, which I think is fantastic. You might think is not so fantastic. Dylan, take it away.
Yes, so I went ahead and entered everyone's names into a random name selector, and today's winner of a Go Direct Motion Detector is Matt H. So congratulations, Matt or Matthew. I will go ahead and email you once this webinar is over. So keep an eye out for an email from an @Vernier email in your inbox, and that'll be me getting some shipping information. So congratulations.
Congratulations. All right, so let's see. Thank you for attending. I'm really glad you all came. I hope that this was at least somewhat useful for you. And if you have any questions, you can always come to the chat on our website, give us a call until 5 p.m. Pacific time, except on Fridays when we leave early, and we're only open till 3 Pacific time on Fridays. And email us at physics@vernier.com. You might reach me, you might reach Tom, you might reach one of the other people here who do physics, but let us know your questions. We'll help you the best we can.
All
So
right.
long, everyone. Thanks.
Bye now.